So let's have this example on beam deflections solved by double integration method. So by the double integration method, compute the slope and the deflection at B. EI is constant. Also compute the maximum deflection in the beam. So here is the given beam. So first, let's compute for the reaction at A, vertical reaction at A. Of course, the horizontal reaction is 0. Obviously, there is no inclined load here. At C, we have R sub C. So summation moment about C equals 0, AY times 8 minus 18 times 5 times 5.5 equals 0. So you'll get AY equals 61.875 kilonewtons. Likewise, summation moment about A equals 0, counterclockwise positive. So R sub C times 8 equals 18 times 5 times 2.5. So we'll get R sub C 28.125 kilonewtons. So we want one moment equation only, so we have to extend the load up to here and neutralize it by also adding load which is equal to 18 kilonewton per meter upward. So the distance from this section from the origin, which is point A, is denoted by x. So therefore, since EI y double prime equals moment, so the moment equation in this section here is 61.875 times x plus 18 times quantity x minus 5 times x minus 5 over 2, then minus 18 times x over 2. Or in short, EIY double prime is 61.875x plus 9 quantity x minus 5 square minus 9x square. So this is the differential equation of the elastic curve. Then integrating once, we have EIY prime equals 495 over 16x square plus 3 quantity x minus 5 cube minus 3x cube plus c sub 1. This is the slope of equation for the slope of any point on the elastic curve. Then integrating again, so we have 165 over 16 x cubed plus 3/4 of x minus 5 quantity to the fourth minus 3/4 of x to the fourth plus c sub 1x plus supposedly c sub 2, but the value of c sub 2 is 0 because the origin A is a support and there's no deflection at A. So remember, the interpretation of c sub 2 divided by EI is the deflection at A. So it is 0. Or you can evaluate it when setting x equals, when x is 0, y is 0, so c sub 2 is 0. Then for the boundary condition, the other boundary condition, when x is 8, y is 0, substitute into this equation of the curve here, then we can solve or evaluate c sub 1. So 165 over 16 times 8 cubed plus 3/4 of 3 to the fourth, because 8 minus 5 is 3, minus 3/4 of 8 to the fourth plus c sub 1 times 8. Then solving for c sub 1, c sub 1 is negative 9,075 over 32. Having found c sub 1, we can now compute the slope or theta at B. So EI theta B is x is 5, of course. So EI theta B is equal to 495 over 16 times 5 square. This is 0. Then minus 3 times 5 cube. Then plus c sub 1, which is negative 90, 75 over 32. So theta B expressed in decimal is equal to 114.844 over EI. So it's positive. That's the slope at B. For the deflection at B, substitute into this equation here. So 165 over 16 times 5 cube plus our minus 3/4 of 5 to the fourth. This is ignored, 0. Then minus 9075 over 32 times 5. So delta B is equal to negative 597.656 over EI. Take note that this value of C sub 1 divided by EI is the slope at A. Then for the maximum deflection, so of course the maximum deflection occurs somewhere here. The value of x is less than 5, if you can analyze, because the uniform load is concentrated on portion AB, so the maximum deflection is expected to occur somewhere between A and B. And the value of X for that is anticipated to be less than 5. So that since the idea is for maximum deflection, the slope is 0, we use this equation for slope, set it is 0, and we ignore this term x minus 5 cube here because we anticipate that the value of x where the slope is 0 is less than 5. So based on the figure and based on your awareness or understanding that the slope should be 0, which is less than 5, because remember the slope at B is positive, so it is inclined upward like this. So the 0 slope should be less than 5. So we set this equation ignoring the second term to 0. So y prime is 0 there. So EI y prime is 495 over 16x squared, then minus 3x cubed, then plus c sub 1, which is negative 9075 over 32 equals 0. So solving for x by trial and error, or if you're allowed to use your high-tech calculator that can compute for a cubic function, the roots of a cubic function, then the only acceptable value of x, which is less than 5, is 3.824 meters. So finally, we substitute it to this equation for um, equation of the curve, and we should expect that the deflection is the absolute value of the deflection should be higher than this delta B here. So EI delta max is equal to 165 over 16 times 3.824 cube. This is ignored, then minus 3/4 of 3.824 to the fourth, then minus negative 9075 over 32 of 3.824. Solving for delta max is equal to negative 668.175 over EI, which is greater than the magnitude is greater than this. So that's why we have to confirm that this is the answer. So for our second example, by the double integration method, compute the slope and the deflection at points B and D. So modulus of elasticity is 200 gigapascals and the moment of inertia is 500 times 10 to the 6 mm to the fourth. So we have a composite beam. The portion AB has moment of inertia twice the given moment of inertia. So BCD has same I. So therefore, we have two equations of the elastic curve, one for portion AB and the other one for portion BCD. So first, let's compute for the reaction at A, vertical reaction, horizontal is 0. Then let's just call this R sub C. So AY times 10 plus 30 times 3 minus 20 times 6 times 7 equals 0. You'll get AY equals 75 kilonewtons. Likewise, summation moments about A equals 0. So we have R sub C times 10 counterclockwise positive minus 20 times 6 times 3 minus 30 times 13 equals 0. So you'll get R sub C equals 75 kilonewtons. So checking 75 plus 75 is 150. Then 20 times 6, 120 plus 30 is also 150. So that's correct. Therefore, we have to set up equation for portion AB first. Then for BCD, we have to extend this load to have a continuous moment equation or a singular moment equation for portion BCD. For AB, this is the section. So we call the distance from the origin A to that section as x. So E times 2I, because the moment of inertia is 2I, times y double prime AB equals 75 times x minus 20 times x over 2, or 10x squared. So dividing everything by 2 because the moment of inertia is 2. So we have EI y double prime AB equals 37.5x minus 5x squared. Then integrating once with respect to x, you have EI y prime AB equals 18.75 x squared minus 5/3 x cubed plus c sub 1. Integrating again, we have EIYAB equals 6.25x cubed minus 5 over 12x to the fourth plus C sub 1x. Supposedly plus C sub 2, but C sub 2 again is 0 because when x is 0, y is 0 at the origin. Then for the other section, for segment BCD, EIY double prime BCD is equal to 75 times x plus 75 times quantity x minus 10 plus 10 times quantity x minus 6 square. This 10 times quantity x minus 6 square is 20 times x minus 10. This is x minus 10. Moment arm x minus 10 over 2. So that gives us 10 quantity x minus 6 square. Then minus 10x square. The other minus 10x square is 20 times x over 2. So integrating, we have 37.5x squared plus 37.5 quantity x minus 10 squared plus 10 thirds x minus 6 quantity cube minus 10 thirds x cube plus c sub 3. Equation 5, integrating again, we have EI y BCD is equal to 12.5x cubed plus 12.5 quantity x minus 10 cube plus 5 over 6 quantity x minus 6 to the fourth minus 5 over 6x to the fourth plus c sub 3x plus c sub 4. Of course, there is c sub 4 because we are referring to BCD. This is, the origin is still here, but it starts with B. So therefore, there is an expected value of c sub 4. Then, for the boundary condition, when x is 10 in this equation here, we can set up an equation involving c sub 3 and c sub 4. Call that equation 6. So when x is 10, y BCD is 0. In particular, y sub c is 0. So 0 equals 12.5 10 cubed. This is 0. Then plus 5 over 6 times 4 to the fourth minus 5 over 6 10 to the fourth plus c sub 3 times 10 plus c sub 4. So simplifying, we have 10 c sub 3 plus c sub 4 is equal to negative 4,380. Call that equation A. Then, there's no more boundary conditions, but we have facts here that at B, which is common to AB and BCD, the slope and the deflection at B for portion AB and for portion BCD are equal. So when x is 6, y prime AB is equal to y prime BCD, and YAB is equal to YBCD. So let's have this equation first. Y prime AB when x is 6, so 18.75 times 6 squared. So this is the anticipated elastic curve. So 18.75 times 6 squared minus 5 thirds of 6 cube plus c sub 1 is equal to 37.56 squared. This is ignored, 0. This is minus 10 6 cube plus c sub 3. So simplifying, we have c sub 1 minus c sub 3 is equal to 315. Call this equation B. Then let's reinforce this equation, YAB equals YBCD. So 6.25 times 6 cubed minus 5 over 12 times 6 to the fourth plus c sub 1 times 6 is equal to 12.5 times 6 cubed. This is ignored, 0. Minus 5 over 6 times 6 to the fourth plus c sub 3 times 6 plus c sub 4. So simplifying, we have 6 times quantity c sub 1 minus c sub 3 minus c sub 4 is equal to 810. Then since we have a value from equation B, c sub 1 minus c sub 3, we substitute it here, 315, then we can compute c sub 4. So 6 times 315 minus c sub 4 equals 810. Therefore, c sub 4 is equal to 1080. Then this value of 1080 for c sub 4, let's substitute this into equation A. Into equation A, 10 times c sub 3 plus 1080 is equal to negative 4380. So c sub 3 can now be solved. C sub 3 is negative 546. Then we substitute this value of c sub 3 in equation B. Then we can now solve for c sub 1. So C sub 1 minus negative 546 equals 315. So C sub 1 is equal to negative 231. Divided by EI, that's the slope at A. Then, we can compute now theta B and delta B. You have the option to use equation 2 for theta B or equation 5, either way, but let's use equation 2, the simpler one, fewer number of terms. Then for delta B, we can use equation 3. So when x is uh, 6, so theta B is 84, so 18.75 times 6 squared minus 5 thirds of 6 cubed plus C sub 1, which is negative 231. So theta B is 84 over EI. And the value of EI is 200 times 10 to the 6. This is gigapascal, so 200 times 10 to the 6 kilonewton per meter square. Moment of inertia, let's convert this to meter to the fourth. So 500 times 10 to the 6 mm to the fourth. And divided by 1000 mm is 1 meter. So quantity raised to fourth. So EI will be equal to 100,000 kilonewton meter square. So that's the value of EI. So that theta B is 84 divided by 100,000. So theta B 84 divided by 100,000 is theta B is 8.4 times 10 to the negative 4 radians. So that's the value of theta B. Then delta B, substitute into equation 3. So EI delta B is equal to 6.256 cube minus 5 over 12, 6 to the fourth minus C sub 1 times, or plus C sub 1, which is negative 231 times 6. So delta B is negative 576 over 100,000 over EI, and this is in meter times 1,000. So delta B is negative 5.76 mm. Of course, delta B is expected to be negative. Then for theta D, so we have no other choice except to use equation 5 for theta B, because we cannot use equation 2 for theta D. That's only for portion AB. So EI theta D is equal to 37.5, 13 square plus 37.5 times 3 square plus 10 times 7 cube over 3 minus 10 times 13 cube over 3, then plus C sub 3, which is negative negative 546 C sub 3. So theta D is negative 5.1 times 10 to the negative 4 radians after you divide everything by 100,000. Then likewise, when x is 13, delta D, EI delta D in this equation, 12.5 13 cube plus 12.5 3 cube plus 5 over 6 7 to the fourth minus 5 over 6 13 to the fourth plus C sub 3 negative 546 times 13 plus C sub 4, which is negative positive 1080. So delta D is equal to negative 18 over 100,000 meter, or in mm, that's negative 0.18 mm. So that we can draw the approximate elastic curve. So that's the elastic curve. That's it. And I hope that you were able to understand the solution.